Hello, young physicists. Have you ever wondered why we say electric charges have potential? Not just because they might do something someday, but because they actually can do work, kind of like a superhero charging up their powers. Speaking of which, why did the positive charge bring a suitcase from infinity? Because it wanted to move against the electric field and pack some energy. Let's dive into what electric potential really means. Electric potential at any point in space is defined as the amount of work needed to bring a unit positive charge all the way from infinity, yes, that far, to that point, moving against the push or pull of the electric field. Now, if you do some work W by moving a charge Q through an electric potential difference V, then the relation simply is V equals W divided by Q. That means the potential V is the work done per unit charge. The unit we use for electric potential is the volt, named after Alessandro Volta, where 1 volt means 1 joule of work to move 1 coulomb of charge. That's like saying you need 1 joule of energy to push a single coulomb to that point. It's important to remember that electric potential is a scalar quantity. It has magnitude but no direction, while the electric field is a vector pointing in a specific direction. In fact, the potential difference relates to the field's direction because the field always pushes charges from higher to lower potential. So even though potential itself doesn't have a direction, its difference helps us understand how the electric field acts. That's the basic idea behind electric potential, energy per charge, waiting to do some electrical magic in circuits and fields. Welcome back. Ever noticed how water flows from higher to lower spots driven by differences in height? Electric charges do something similar but driven by potential difference. Potential difference between 2 points is basically the work done to move a single unit positive charge from one point to the other. Imagine pushing a tiny positive charge from point A to point B while overcoming the electric forces acting against you. Mathematically, this is written as V equals V sub B minus V sub A, which means the potential at point B minus the potential at point A. This is also equal to the work done, W sub AB, divided by the charge Q that you moved. So, the equation is V sub B minus V sub A equals work done from A to B divided by Q. 1 volt, remember, is 1 joule per coulomb, so it tells us how much energy each coulomb gains or loses in moving from one point to another. This potential difference is what actually drives the electric current in a circuit. The greater the potential difference, the stronger the push or electric pressure on electrons, making them move faster. So, next time you switch on a bulb, remember it's this potential difference that's pushing those invisible electrons to light up your room. Let's unravel how electric fields and potential are related, like two sides of a coin. Imagine you're hiking up or down a hill. The steepness of the hill tells you how quickly the height changes with distance. Similarly, the electric field E at a point measures how fast the electric potential changes over distance. In fact, for a uniform electric field, E equals minus the change in potential, delta V, divided by the change in distance, delta D, that's E equals negative delta V over delta D. The negative sign here is super important. It tells us that the electric field points in the direction where the potential decreases the fastest. Picture a graph where potential V decreases linearly as you move along distance d, a gentle slope downward. The slope of that graph is exactly the electric field strength. This relationship helps us calculate the electric field if we know how much potential changes over a given distance. Just like a steep hill means a strong gravitational pull, a steep potential slope means a strong electric field pushing charges along. Let's switch gears and imagine electricity through the lens of something more familiar, water flowing through pipes. Electric potential is like the height of water in a tank. The higher the water level, the more pressure it can exert to push water through pipes. In electricity, a higher electric potential is like that higher water level, pushing charges to move. Voltage difference is just like the water pressure difference between 2 points in a pipe. When there's a pressure difference, water flows from high to low pressure. Similarly, when there is a voltage difference, charges flow from higher to lower potential. Just as water rushes down a slide due to a pressure drop, electrons drift through a conductor because of the potential difference. This handy analogy lets us picture invisible electrical processes by thinking about something we can easily see, water flowing downhill. So, whenever you think of voltage, picture water tanks and pipes with pressure differences pushing the flow. Alright, time for some number crunching. Don't worry, this will be fun. Say you have a charge Q of 5 coulombs and the work done W to move this charge is 100 joules. What's the potential difference V in this case? We use the relation V equals W divided by Q. Plugging in the numbers, V equals 100 joules divided by 5 coulombs, which gives us 20 volts. That means it took 20 joules of work to move each coulomb of charge. So the potential difference between the points involved is 20 volts. This simple calculation shows how voltage connects work and charge, giving us a clear numerical idea of how much energy each charge carries between 2 points. Next time you charge your phone, think about how the battery creates just such potential differences to power it up. Now, where do these potential differences come from in real life? The answer lies in electrochemical cells or batteries. A cell converts chemical energy directly into electrical energy, creating and maintaining a potential difference across its terminals. The maximum potential difference a cell can provide when it's not connected to any circuit, meaning no current flows, is called the electromotive force or EMF, usually denoted by the Greek letter epsilon. But when you connect the cell to a circuit, the potential difference across its terminals drops a bit because of the cell's internal resistance. This is expressed as V equals epsilon minus I times R, where V is the terminal voltage, I is the current, and R is the internal resistance. Batteries, of course, consist of multiple cells connected in series to increase voltage or in parallel to increase current capacity. If you look at a circuit diagram, you'll see the cell connected to a resistor and a voltmeter measuring the potential difference across the resistor. This practical setup is exactly what powers our gadgets every day. Let's get precise about units and dimensions, the language of physics. The C unit of electric potential is the volt, symbol V, which equals 1 joule per coulomb. That means 1 volt is the potential difference when 1 joule of work is done in moving 1 coulomb of charge. If you remember, the dimensional formula of potential is mass to the power 1 times length squared times time to the power minus 3 times electric current to the power minus 1. That's m to the first, L squared, t to the minus 3 and a to the minus 1. Understanding these dimensions helps us check our equations and convert units correctly when solving problems. Finally, when measuring potential difference with a voltmeter, always make sure it's connected in parallel with the component whose voltage you want to measure and that it ideally does not draw current itself. This ensures an accurate measurement without affecting the circuit. Let's quickly recap our journey through electric potential and potential difference. Electric potential at a point is work done per unit charge, written as potential V equals work W divided by charge Q, and 1 volt equals 1 joule per coulomb. The electric field E equals negative change in potential delta V divided by change in distance delta D. Potential difference between 2 points A and B is V sub B minus V sub A, which equals the work done moving charge Q from A to B divided by Q. In cells and batteries, Terminal voltage V equals EMF epsilon minus current I times internal resistance R. Remember, electric potential is a scalar quantity representing energy per charge, while potential difference causes current flow and is generated by cells, generators, or induced EMF. The electric field is a gradient of potential, so stronger fields mean sharper potential changes over space. Finally, voltmeters measure potential difference, always connected in parallel to avoid disturbing the circuit. That wraps up today's concept. Physics is far more fun when you can laugh and learn together. See you in the next session.